Okay. Everybody doing good? Y'all ready for the holiday? Yeah? All right, so reminder, today we're going to review for the exam. We do not have class on Thursday, obviously. We will have our exam on Tuesday when we come back from Thanksgiving. That's what you wanted, so that's what's going to happen. And then that Thursday after that is our last day of class before the final. So we'll see how much we can get done in that class. So fun. The Thursday after this one is our last day before the final is the week after that. So, all right. So today, review. There's one topic that we started talking about at the end of class last time that I want to wrap up. So I'm going to take the first 15, 20 minutes of class to kind of reiterate that idea, which was half-life. We talked about half-life of a bone. We tried to estimate how old a bone was. Remember that? Or something? Yeah. So we were using the carbon-14, it's called carbon dating, trying to find out how old something is. But that's not the only times we use half-lives. So I wanted to talk, this is almost like going to be like a history lesson today a little bit. 1986 in the former Soviet Union in a city called Chernobyl. I believe it's a city, yes. Anyone know what happened there? There's a nuclear meltdown. So they have a nuclear power plant. We have nuclear power plants here in the United States. They all have these like reactors. They're called nuclear reactors. And basically what they're doing is they're taking highly radioactive materials like plutonium, 241 is what they were using in Chernobyl. And they're using nuclear reactions, the same things that we make nuclear bombs from, but they control the reactions and create energy to power your lights and, so that's what they were doing over there, 1986, right? And when you're trying to control these nuclear reactions in the core of this reactor, the temperatures in there get like extremely high, like temperatures close to like the surface of the sun temperatures. And you have to control this, you have to cool it. There's a lot of things that have to be done right. And in 1986, they lost control of the reaction, and they weren't able to contain the temperature anymore. There was a lot of things that had to go wrong, that went wrong, but basically they had a meltdown. They call those meltdowns. And so the plutonium that was in the core of the reactor became so hot that it was almost like if you've ever taken like a hot knife through butter, and first it blew up, okay? So it blew up and it threw a bunch of material everywhere. And then the bad stuff, the real bad stuff, kind of just melted into the ground, started going down to the ground. And there's, the explosion threw a bunch of radioactive material into the air, and that wound up killing a bunch of people that lived there. They had to evacuate the city. And to this day, nobody lives in Chernobyl, all right? You go there, it's a ghost town still. It's weird. If you look it up on Google, do Chernobyl, like pictures and stuff, and you'll see like trees growing out of buildings, and it's just like a weird, weird, weird place. All right, yes?
Wait, did you know that there's actually like the older generations that like were there like in their 70s, 80s, like just refused to leave. So they ended up living like in all that radiation, like in run down shacks, spend the day to die. That's a big.
Yeah, they're all zombies now though. And so, yeah, I'm sure there were some people who stayed. There's a certain radius at which it's safe, all right? And the bad thing about nuclear material like plutonium is that what it does is the same thing that happens to like if you put, I don't know, a hot dog in a microwave, right? It heats it up from the inside, right? There's these little waves that you can't see that go in there and heat up the food. Well, radiation's the same way, but it goes into your body and it changes your DNA. So it goes in there and alters your double helix DNA code in your cells of your body, and then your body starts to basically make mistakes. So your cells start to duplicate, but they're damaged, right? So they're creating a bunch of damaged cells. So it's like cancer. creates cancer in your lungs, different things. Depends on how you get the radiation into you. Bad stuff.
Happens with a lot of superheroes, like in the superhero movies.
What's that? Yeah, like superheroes' DNA is different than us because that's what makes them super, I guess, yeah. So, but the radiation changes it in a bad way, not in a good way. You become dead, basically. All right, so radiation, this is bad stuff, right? And the plutonium-241 is really the main source of it. There's other sources too, but. So what they did, I've always found this to be fascinating because once they figured out what happened, they sent in a crew of firefighters, basically. And they said, what we're going to do is we're going to take some concrete trucks out there, some big old, those mixer trucks with concrete. We're going to take them out there. And by this time, the core had melted down. So you got this plutonium down here, and it's melted down into the earth a little bit. And they said, what we're going to do is we're going to kind of just wheelbarrow in there concrete. We're just going to start filling this thing up with concrete and just entomb the uranium or the plutonium into concrete. And that will at least contain it better than just letting it sit there, right? So all the guys who basically did that, I mean, that was like a death sentence right there. Like, you're going in, you're going to live for a while, but you're not going to live much, too long. You got maybe a month or two after this, and that's it. So all the guys that went in there, knew what was up. But, they did it, and they saved a bunch of other people by doing that. So that uranium's still there, right? Still underground. And anybody have any idea how much, I said uranium, plutonium, how much plutonium was actually there in the original meltdown? Anyone have a guess?
Like, is it more than?
Just give me, what do you think? No, it doesn't grow. It decays. It has a half-life, which we're going to talk about in a minute. So it is going away as time goes on. But how much do you think was there originally? Any ideas? 3 tons? Ton is like 2,000 pounds, right? So 3 tons, any others? No? 12 pounds. 12 pounds. That's like your backpack. Well, I don't know, it's probably more than 12 pounds. It's like, it's not much, is it? That's what makes nuclear weapons so bad, and you don't need a lot of it to cause a lot of damage. So you've got 12 pounds of plutonium-241 sitting in the ground, and it has a half-life of 14 point... This is the good news, I guess, if there's any good news. I have it written down here. 14.4 years. Okay? So plutonium -241. Don't worry about the -241. There's all different types of plutonium. There's uranium, and different weapons are made out of different things. But it's all bad stuff, all right? So this plutonium-241 has a half-life of 14.4 years. Okay? And will y'all just give me a second real quick? I need to step out for just a second. Y'all can think about Chernobyl real quick. Okay, sorry about that. All right, so half-life of 14.4 years. What I was trying to get across to you last class is that whenever we have half-lives, we can always model what's going to be happening to this material with the same formula that we were using for the interest, the PERT formula, but it's been modified a little bit. So the formula I gave you last class was A equals A with this little 0 down here, e to the kt. Do y'all remember that? Which reminds me, on the test on Tuesday, you were allowed to bring a cheat sheet. Remember that? No penalty. Remember me saying that? You may not have worked out problems on this, okay? You can't take the review I'm going to give you today and just work it all out and call that your cheat sheet. You can have steps and procedures, you can have all the formulas you want, all right? But nothing worked out in detail. Yes?
The part we're going to have
Final, yeah, we'll do some sort of same thing. I don't know though. I might charge you for it, like a couple of points or something. But we'll see. All right. All right. So that's the formula. So please pay attention to this because this is what you're going to need to know how to do on the test on Tuesday. I'm going to give you a problem like this, and let me read you the problem off the review. I don't want to hand these out yet because people will start working on them. Number 13, the last problem on the test. The half-life of plutonium-241 is 14.4 years. If 12 pounds of plutonium-241 was released at Chernobyl in 1986, how much is there now? That's the question. How much is there now? So there was 12 pounds initially, right? And we want to know how much is there now. Well, to do this, you must use this formula right here. And the first step to using this formula is to find K. Right? That's your first step. We must find what K is. K is called the growth constant or decay constant. In this particular case, it's decay because plutonium, as time goes on, it decays out, kind of like a fire burns out over time. This stuff starts to get less bad, or there's less of it over time. So we're going to find K first. So I'm going to find K. Now what I know is that the half-life is 14.4 years. That means that if I start out, this was my starting amount, right? If I start out with 100%, then 14.4 years later, I should have 50% or half, right? So I'm going to rewrite this formula right now like this. 1/2 equals 1 times e to the k times 14.4. So if I give you a different problem, because I'm obviously not going to give you the same Chernobyl problem on the test, what you're doing on this first step to find K is you will always replace the left side with 1/2, because half-life means this will be half, all right? You'll always replace this with 1 because you're always assuming you start out with the full 100%. E will always be E, K will always be K, and this number right here is the half-life for that particular substance. So if it's plutonium-241, it's 14.4. If it's carbon-14, it's whatever, 5,000 something years. I will give you that information. So I will give you the half-life, all right? So you set this up, and when you look at this, the only variable in the problem is K, right? That's the only thing there. So you can solve for K. So I'm going to rewrite this as 1/2 equals, I don't need to write the 1, right? Because 1 times anything is itself. But I am going to rewrite K times 14.4 as 14.4 K. So we like to put the variable behind the number, so I'm going to put it that way. Are we good? Questions? Now, to solve for K, how do we solve for a variable that's up in the exponent? We have to bring it down, right? And the only way to bring it down is with the natural log, right? Move it out front. But be careful. What I see people do on tests, they just take it and they just drop it down. And you can't do that. You have to bring in the natural log on both sides first. All right? So I'm going to bring in natural log of 1/2 on the left side. And I'm going to bring in natural log of e to the 14.4k on the right side. On the left side, natural log of 1/2, feel free to do that on your calculator now. Make sure you can get the correct answer. It should be negative 0.693147186 or 806, something like that. And I would ask that on the test that you just go as many decimal places as this will go on your calculator. All right? That way you'll be pretty accurate with this. If you round that, it's going to throw it off big time right now. 0.6931471806. That's the left side. Now what about the right side? I told you last class there's two ways to look at this. These two together are 1, right? But that's if it's just those two together. Two ways you can look at this. Drop this out in front right now. If I drop that out in front, I get 14.4k, right? and then natural log E times natural log E. And natural log of E is 1. That was a property. That's 1. The other way to look at it is that if you ever have natural log of E to something, these kill each other off and you just get this something. That was a property I put on the board a while back. Natural log of E to the X is X. Do you remember that property? Natural log of E to the X is X. So it's natural log of E to the X is just X. So you could just write on this next line 14.4 K. Got it? Any questions? Divide by 14.4 on both sides, and you'll get K. So divide by 14.4, and I get negative 0.048 135 2209 is K. Any questions? Everyone's...
Get the decimal negative one? I get the same thing I got with 181.
You got what?
Instead of 180, I got 181.
Oh, right here, that's fine because your calculator rounded. I said go as far as yours does. So if it goes to 181, just use that. All right, I said the first step is to find K, right? So we know now what this number should be. Okay? So here's what we're going to do. I'm going to rewrite that formula. And I'm going to replace the K with this number. It's going to look ugly. Negative 0.04813 and then times T. So our entire goal was just to figure out what this K was, right? That was the initial part of the problem. Find out what K is. Once I know what K is, I rewrite the formula. And this formula is now the formula that we can use for plutonium-241. All right? If somebody tells me how much time, I can figure out how much is there. Or if someone tells me how much is there, I can figure out how much time it took for that to happen. Understand? Okay. So when we look at this and we look back on the problem, I asked us, how much is there now, right? How much is there now? That was the question. If 12 pounds of plutonium-241 was released at Chernobyl in 1986, how much is there now? So how can I use this to answer that question? Do you know how much was there initially? Remember, that's the initial amount. Like that's the amount you normally would say you put into the bank to start. Well, we're putting 12 pounds of this plutonium in to start. So I can rewrite this as 12, right? Agreed? All right. They want to know how much is there now, which means they want to know, that's like me saying how much money would be in the account, right? Now, if you put money in back in 1986, I want to know what A is, right? To figure out A, I'm going to need to know the amount of time. And this time is always measured in years. So what am I going to put in there? 2016? No, 30, because you have to look at the time that you started at, 1986, up to now, 2016, is 30 years. Agreed? So it's important to understand that T is going to be replaced with 30. So the amount here should be 12e to the negative 0.04813522209 times 30. So go ahead and do that on your calculator. I'm gonna multiply these two together. And so you should get the amount the amount of plutonium will be 12 times E I'm getting negative 1.4440566, something like that. Anyone else getting that? So what would I do next? We want to know what A is, right? So A is already solved for. We just have to evaluate this. That means I need to get on my calculator. I need to do e to that power, which I have a key for, right? Find your e key and do e to the negative 1.4440566. So you should now get 12 times, and all of this right here becomes 0.235968. Got it? I can keep going more decimals if I want. I'm not going to have any mercy on you if you can't figure out how to do this on the test. All right? If you can't, because every time we've been in class, I've said this is where you need to practice. You need to bring your calculators. So if you have any questions on how to do it, now's the time.
I didn't get that number.
Did you use a negative on your power?
Yes.
Let me see how you typed it. You put 14, not 1.4. See it? All right, so now I'm going to take 12 and multiply it times this number. So you get 2.8316-ish. So about, what, almost 3 pounds still there, right? Approximately 3 pounds. That's how much is still there. Started out at 12, 30 years later, you've got 3 pounds still. One thing to remember, though, about exponential decay is that exponential decay looks like this, doesn't it? And it approaches 0, but it never gets there. And so if we go back to Chernobyl 30 years from now and check again, there's still going to be some there. And if we go back 3,000 years from now, there's still going to be some there. And the way I could figure that out is just keep changing this number, right? Here I use 30. If I want to see how much is there in 300 years, I add another 0, 3,000 years. It's never going away. No, that's right. So let me do it. 12 e to the negative 0.481352209 times, what do you want, 300 years from now? 3,000 years from now. Whoa. I typed that in wrong. I forgot my parenthesis there. It's not going to be a lot. Oh, wow, actually, it's not a lot at all, but it's still there. It's like 0.00000 with like 62 zeros. So it's basically gone. Look, same thing happens when people take, like, if anyone has had someone in your family or knows someone who's had like chemotherapy for cancer, you know, basically you ingest radioactive material in a way that the idea is that it's going to go kill all the bad cells, the cancer. But simultaneously, it's going to kill your good stuff too. It's like you're trying to kill both, you know, kill one off without killing the person is what chemotherapy is. And it's radioactive material. And so theoretically, it never goes away once it's in your, you know, body. But it decays fast enough. The half-life of the chemotherapy is fast enough that you get to negligible amounts in your body that don't affect you. So it's like we all have things in our body right now that in large quantities would be bad, right? Like everyone knows like cyanide will kill you, right? But we all have a little bit of cyanide in us. We all have a little bit of lead in us. You know, there's things we have, but it's like, you know, infinitesimally small amounts. Do you all know that when you eat your cereal, that there is an accepted amount of like animal byproducts that can be in there? Like next time you're eating your bowl of cereal, I want you to realize that when they had this big drum with like 10,000 pounds of grains, there could have been a rat or two in there, and it could have got ground up with everything else. It's true, okay? You're allowed to have a little bit of bad stuff in there, because it's impossible to not have it. You can't have, you look at these silos on the side of the road, like if you've ever driven out to like Castroville or something, big silos of corn or whatever, they've got, tons and tons of stuff in there. You're not going to keep all the bugs out, right? It's impossible. So when they process it, that stuff gets processed too. It's okay to have trace amounts, but it has to be trace amounts. You don't want to find a rat leg in your Frosted Flakes, right? Hey, I'm just being real with you, okay? My daughter found a fly or a gnat or something in her Chinese food the other day, and she got freaked out, and I was like, man, that's a gnat. Like, you've eaten a lot worse than that. She doesn't realize she has, but you eat a lot of stuff that you don't realize you're eating. It's not that bad. Okay, so do y'all think y'all could handle a problem like that? I give you a half-life, and then you go on to answer the question about, how much of it's going to be there after a certain amount of time. Two-step process, find K. Once you have K, then go back and set up the formula to figure out the amount. All right. We're planning a field trip for next week to Chernobyl if anyone's interested. No? It's a one-way ticket. All right, here's a review that I promised you. We still have 45, 46, 47-ish minutes. I have not worked through this, so would you all like to, would you like me to go around the board again like I've done in the past and just put the answers up, or do you all want to work on the boards? How do you want to do it? You want me to work on the boards? Anyone object to that? You object? Okay. All right, so just a quick discussion of this. You're going to be asked to sketch an exponential function and simultaneously sketch the log function at the same time. Why would I ask you to sketch both at the same time? Yeah, because of the way that you graph them, right? You graph the exponential, and to graph the inverse of it, you flip the x and y coordinates. So that's why I ask you to do them together. I give you two of those just so you can practice. Then from there, it's your simple interest, money into an account for a certain amount of time. Number 3 and 4 are like that. Number 5 and 6 are logarithms just on your calculator and then without your calculator also. 7, 8, 9, and 10 are solving exponential equations. 11, 12, 13 are all word problems that you wind up solving exponential equations. All right, that look fun? You're stressed out a little bit?